Hey everybody, welcome back. We're gonna go over practice 1. So you guys should have just finished taking notes. So remember, we're not doing any of the labs or anything like that till I get back. So it's just kind of seeing how this is done. So you had notes with all of these different examples. And then now we're going to actually practice it. And if you need to, this is, kind of the walkthrough. So let's get into it. Now, I'll let you know, I did just record this video and then find out after the whole thing that it didn't record. So if I am going too fast through some of this, that's why, but just let me know in the comments or something if you need to see something a little bit more in depth. But remember, the process for these is always draw a picture if you want, but start with a force diagram and then figure out the rest of it from there. So number 1, we have an elevator that's moving up at a constant velocity. So right away, I know constant velocity, really important to know, because if something is going at constant velocity, Newton's first law tells me that that means that there is no net force. So the net force is equal to 0. All right. So I know all the forces, when you add them up that are acting on the object, they all cancel each other out. The passenger has a mass of 85 kilograms, so that's important to know. So construct a force diagram for the passenger. So here is the passenger. So I'm going to draw only forces that are acting on the person, right? So I can use the person, I can squish them down into a dot. I have the force of gravity that is pulling straight down towards the earth. Sometimes we call that weight. I'm in the mood to call it force of gravity right now. And then right here, I have, there's the ground. And the floor is pressing up into the person. And we call that force a normal force. Okay? Now, what do I know? I know because this thing is going at constant velocity, if these are the only two forces that are acting on this thing, then because the net force, the sum of those forces is 0, these two, since they're going in opposite directions, must be canceling each other out. And you think about it, the only way mathematically that can happen is if they are the exact same size. So I can put little tick marks to show that these are in fact equal to each other in magnitude. And I can even write a little reminder to myself. The normal force is in fact equal to the force of gravity. Okay. And that's it. Calculate the force the floor exerts on the passenger. So that is that normal force. We want to figure out how big is that force. Well, what do we know? The only real numerical thing we know here, we know what the velocity is. It doesn't really do anything for us. But we do know the mass. And that's important because if you know the mass of your object, you can figure out what its weight or what its force of gravity is by Fg equals mg. And remember that m right there is mass. And this is called the gravitational constant or the gravitational field strength. And on Earth, that's about 10 newtons per kilogram. Okay, so calculate the force. Well, if the normal is equal to the force of gravity, like we just wrote, and the force of gravity can be calculated by mass times g. Well, we know the mass, it's 85 kilograms. Okay, we know g on planet Earth, like exactly, it's more written as 9.8. We like to round to 10. I like to round to 10 to make our math a little easier. So 10 newtons per kilogram. And newtons per kilogram, it can also be written as meters per second squared, right? And one of the previous videos I had, the review over Newton's second law concepts, there's a portion of that video that goes over the units. So if you're kind of iffy on that, I'll put the link to that down in the description. But go ahead and watch that because it goes over how newtons per kilogram and meters per second squared kind of turn into the same thing. But now we see why 10 is nice. 85 times 10, 850. And what would my units be? Well, here I got kilograms. There in the denominator I have kilograms, so my units end up being just newtons. Okay, so that would be 850 for the force of gravity, and then also 850 for the normal. And because those are the exact same, size of force, they cancel each other out. And therefore, it doesn't mean our elevator person is totally still. It means that there's just not enough force to make them speed up or slow down. It's going to just keep doing whatever it was doing. Okay. Now, number 2, that changes a little bit. The elevator is now accelerating upward, but accelerates is the important part. That tells me that the net force now is not equal to 0, which means I can set up Newton's second law. Net force equals mass times acceleration. So we want to make a force diagram. Now, if they're accelerating up, I have this force of gravity, right? And it's the same person, right? So same person, same mass. Now, their force of gravity, their weight, does not change at all throughout the course of this. So if they're 85 kilograms, then I know right away they have a force of gravity of 850 newtons. Okay, so that doesn't change at all. But if they're accelerating upwards, I know that this upward force needs to be noticeably bigger than the downward force, right? That's the only way that it's going to accelerate up. So I know this. I don't know this number yet, okay? But that's what my force diagram is going to look like so far. So now part B, write an equation for the vertical forces. So we start with Newton's second law, net force in the y direction, because it's vertical forces, equals mass times acceleration in the y direction. And now we can plug in the stuff. So I like plugging in all the variables and everything first. So anything going up, we normally say is the positive direction. Anything going down, we generally say is the negative direction. Okay. So up would be the normal. So positive normal force plus, because it's a summation, right? It's a sum, plus anything going down. Well, force of gravity is going down, so it's negative Fg. Now, one little trick, okay? As soon as we know Fg, generally you can just replace that with mass times gravity, the term mg right there. So let's rewrite it real quick. N plus minus is negative mg equals acceleration in the y direction. Okay, so there is my equation for the vertical forces. All right, all I did was turn that Fg, all I did was substitute that little piece in. Okay, is it wrong if you don't substitute? No. All right, having done this a bajillion times, I know we're probably going to need to plug stuff in later. Now, calculate the force the floor exerts on the passenger. That's saying calculate for the, solve for the normal force. So my goal here is to isolate this normal force variable, right? So it becomes just like good old algebra 1. I want to get this in all alone. So what I can do, I can add this term mg over to both sides, right? Those cancel. And then I have normal force left over here is equal to m times acceleration plus mg. Now you could absolutely just plug and chug right here, plug in 85 for the mass, and then these things, but you'll notice we can clean this up a little bit. There are like terms. This m is the same on each one, so again, like to make the math stuff as clean as possible. Okay, and now we can plug and chug. The mass was 85 kilograms. The acceleration they told us was upward, so positive 2. And the g was 10. Now, Mr. Cunningham, why isn't the 10 negative? Because it's for the thing that's going down. Well, if you remember, we already accounted for that negative sign, right? When we made it negative force of gravity right there. The reason why we did that was because this thing was pointing down. So we don't want to plug in a negative twice, right? So the whole reason there was that minus sign was already because we took into account its direction. I don't know if you can hear the newest member of the family in the background, but she's crying. Let's see. So what is this? 85 times 12. That's 850 plus 170, 1,000 and newtons. Okay. So that would mean that, you know, downward right here, if we were going to finish this force diagram, 850, and then this is 1,020 newtons. So looking at this, it's good. This would be accelerating up because there's more force going up than there is going down. So it would accelerate upward. Okay. Number 3, upon reaching the top, the elevator now accelerates downward at 3. So there is an acceleration. Okay. Downward means it's probably going to be a -3 acceleration. All right, so construct a force diagram. So it is accelerating downward. That means that we need to have more force going down than we do going up. So we can take that into account when we draw our force diagram. Remember, the force of gravity does not change. The force of gravity depends on the mass of the person, right? So it was 850 for the first two. It's still an 85 kilogram person. Whoa. So force of gravity still going to be 850 newtons. Okay. But this upward force now is going to be smaller. It's still a normal force, but now the floor of that elevator isn't holding them up as much, which is why they're going to accelerate downwards. Okay. So there's our force diagram so far. We start again with Newton's second law here. All right, and it's going to be really similar to that last one. It's just different values going in. Calculate the force the floor exerts on the passenger. Well, that's, again, me isolating this normal force variable. So same exact steps as before. Add those terms over. I'm skipping one little simplify. If you need to see that step, just reverse, rewind a couple minutes and see what I did in the previous one. And then it's plug and chug. All right, so the normal force is equal to the mass, which is 85 kilograms. The acceleration now is -3. Oh, hello. Hold on. Careful. No. Abby, say hi to the camera. Up there. Up there. Say hi. This is not the new one, by the way. This is the first model. All right. Where were we? 85. The acceleration we said was -3. So I got to plug in that -3 right there. And then G is 10 again. Right? So this ends up becoming 85 times 7, which 595 newtons. So if we plug that in, just to make sure that, we keep track of everything, this looks good. This would be accelerating downward because I have more force going down than I do going up. Okay. While descending in the elevator, the cable suddenly breaks. After the cable breaks, how big is the force on the passenger? So we can use this picture up here again. Imagine this is your elevator. And right now, especially for this first one, right? The elevator is in the way of the person falling right there. Right? If that floor did not exist, the person would just drop. The elevator gets in the way and pushes back up on them with what we call a normal force. So if all of a sudden this cable breaks and that cable snaps and it's gone, that means this floor that was holding the person up and exerting that normal force upward on the person that floor is now gone, which means the normal force is now gone. So the normal force, the force of the floor on the person, is going to now be 0 newtons. It's not there. Okay? So if you think about that force diagram, would now look like only the force of gravity. Mm-hmm. And anytime this situation occurs, that is called something in free fall. Not right now. Thank you. Okay. So if something is in free fall, it's going to have a acceleration of gravity, 9.8 or 10. Okay, so and you can even solve this using Newton's second law. It's almost like a proof, but if the sum of forces, well, the only force here is the force of gravity, so Fg, right? What's our substitution for the force of gravity? Mg. And if you take a look, there's those m's on this both sides. Okay, so A, the acceleration, is equal to the pull of gravity. So, which, you know, we call usually 9.8 if you're trying to be exact, or about 10. 1 second. Number 5. This one actually pretty similar to the little tangent I just went on, but a 70 kilogram skydiver jumps out of an airplane. So we have their mass, right? Which right away, you know, if you have their mass, you can calculate their force of gravity or their weight. Immediately after jumping, what is the skydiver's acceleration? So they are falling, right? There's no air resistance yet. They just stepped out of the airplane. So their force diagram would look just like that one we just drew, right? And if I know their mass of 70 kilograms, I know right away 70 times 10, that's 700 newtons. What is their acceleration? So you could 2 ways, right? First way, knowing immediately force of gravity is the only force acting on this object, so it's going to be just 10. But we could also do basically this little thing. It's going to look the exact same. So we know that the acceleration is always 10 meters per second squared, and that's going to be negative 10 because they are going down, right? So negative 10 is how we could say that numerically. You could make sure you said 10 meters per second downward, right? Acceleration is a vector, so you need to have the number and the direction attached to it. Okay, so however you make sure you have it known that it is 10 meters per second down. Upon reaching a downward velocity of 100 miles per hour, 300 newtons of air resistance resists the skydiver's motion. Draw a force diagram. So what did we say? We said, so now they have that same exact force of gravity, right? 700 newtons. But now there's this upward air resistance force. We could probably call that, drag or friction. And it's 300 newtons. And, just like normal, anything going up is positive, anything going down is negative. So, if I want to solve for their acceleration, right? How forces relate to accelerations, that's all Newton's second law stuff. So start with Newton's second law. Now I just need to add these up. I have positive 300 because it's going up, and then plus negative 700, so minus 700 newtons. The mass is 70 kilograms. I don't know what the acceleration is yet, so we can do a little simplification. solve for acceleration. So divide both sides by 70 to get that A all alone. And we're left with 400 divided by 70. That's going to be 5 point something. 400 divided by 70. 5.71. All right, and there's a couple pieces of information in this answer, so it's important for us to know. 5.71 meters per second squared. That means it goes that means that the velocity changes 5.71 meters per second every second that skydiver's moving, right? That negative means that the acceleration is directed downward, okay? So the velocity is changing downward 5.71 meters per second every second, right? So if they're already going down, they're going to be going faster and faster. If they're going up, because that acceleration is directed down, it's going to slow them down, okay? But that negative is the direction. So it's important to remember, you know, that negative is giving you the direction of that number. Okay. Last problem. Draw a force diagram for a car that exerts 5,000 newtons of traction on a level road while being opposed 1,000. So we got the mass. So this one's got a few more things going on, so I'm just going to draw a picture. A very accurate artistic rendering. Okay, what do we got? We got the force of gravity. We have a normal force. Okay, I know that there is a 5,000 Newton force making this thing go forward. And then there are 1,000 newtons of force resisting it, so going the other direction. Okay. So there's our force diagram. There's a couple more things we can figure out. This is where the problem solving, like the puzzle solving, comes into play. Whoop. Just happened. We're still good. Okay. Remember, there's horizontal forces and there's vertical forces. There are only two vertical forces, one going up, one going down. So what I want to think is, well, in the vertical direction, is this car accelerating? And the answer to that is no, because if I think about it, you know, it's not accelerating downward while driving, and it's not all of a sudden taking off and flying away while driving. So I know that the net force in the y direction is equal to 0. So what does that mean? That means that the normal force right there must be equal to the force of gravity. All right, so I can put those little tick marks on those forces to show that they are equal in magnitude. Okay, now in the x direction, I know it's accelerating, right? There, I can just look at the forces. There's 5,000 to the right, there's 1,000 to the left. That's really easy to figure out. The net force is going to be 5,000 minus 1,000. It's going to be 4,000, right? So we can set up our force equation like so. All right, and then it asks, what is the direction? What direction is the car accelerating? Well, in the x direction, like we just said. Now, there's two x directions, positive, negative. So we want to know, it's good to know which way is positive. To the right's usually positive. To the left is usually negative. So this thing is accelerating where there's the bigger force. So that is going to be the positive x direction. Set up the force equation for the car in that direction. So we started with that, right? What we can do now is actually sum the forces in the x direction. So that would be positive 5,000 minus 1,000 newtons equals, the mass was 900. We don't know the acceleration. So this equation is the answer to part B. Okay. C says actually solve this for the acceleration. So I'm actually going to just continue on right here. So this would be 4,000 newtons equals 900 times the acceleration. All I need to do now is divide both sides by that 900 to get the answer. All right. So the answer ends up being 4.44 meters per second squared. And double check, is it right that I have it as positive? Yes, because it's accelerating in the positive direction because that's where there's more force. So my answer for the acceleration should be positive. Okay. So remember, this part is for part B, and then the rest of this was all for part C. Okay. Number 7, if you're feeling confident in this stuff and you want a little bit of a challenge, you can go ahead and try those out, but we're not getting to those quite yet. So don't stress too much about them. But hopefully this was helpful. If you have any problems or you want something explained a little more, like I said, leave it in the comment. And other than that, I will see you guys when we get to the next one, which is practice 2. It's basically the same thing. All of these really are just practice setting up Newton's second law. Newton's second law purely is like a problem solving. It's like a puzzle, right? You figure out what do you have, what can you solve for, what things do you like, where can you put what. So rather than having all of these like A, B, C, D questions, practice 2 is more like, here's the word problem, solve it, right? It gives you a problem, determine the lift force. Gives you a problem, do the groceries, stay in the bag, right? So they're more just like, here's a problem, solve it. But we always want to, you can choose to draw a picture, but you're always going to need a force diagram, right? So you always start these problems with force diagram, then from there you get going, okay? All right. Well, I will see you all later.